previous lecture, we discussed the transport characteristics of ultra-small or mesoscopic tunnel junctions. In this lecture, we will discuss the transport properties of devices, namely the single electron box and single electron transistors. These single electron transistors are also corner dots. Also corner dots. And we also will discuss the transport characteristics of these devices, namely the Coulomb blockade and the Coulomb diamonds. Then we will finish it with overviewing the metallic and semiconductor quantum dots. A single electron box is a small conducting region which is capacitively coupled to a voltage source and also tunnel coupled to the source of electrons. This is a circuit representation. This can be coupled to two different voltage sources also, but the only point is there should be a common reference for it. Okay. And here is a picture, a scanning electron micrograph of one of the device. But what you're seeing here is you have a small conducting region here which is connected to source of electrons, source of charge through some tunnel barrier, which are not really clear in this picture, but there are tunnel barriers at these points. And there are also gates which are capacitively coupled to this small conducting region. Okay. This was actually a superconducting device, but if you apply a magnetic field, you can make it a single electron box. Now let's look at the energetics of this device. So what you have is a quantum dot which is capacitively coupled to an electron or a gate. So number of electrons on the region quantum dot, which I have represented by this tunnel junction here, is discrete. But the charge that the gate is going to induce on this island is continuous. Because that is an induced charge. Okay, but this is the actual number of electrons. N is the actual number of electrons on the island. So the total electrostatic energy of this island is given by this expression, where Ne represents the discrete number of electrons present and CgVg represents the induced charge. Okay. This is of the form Q square by 2c sigma. That is the charging energy, or that is electrostatic energy of the quantum dot with an effective total charge of CgVg minus Ne. Cg is the capacitance of the gate and Vg is the voltage. Okay. Now, this is an equation for a parabola, which is as represented here. And this parabola is centered at Ne. Now, when you vary this gate voltage, what you are doing now is you are lowering or rising the electrostatic potential of the dot in a continuous manner. So you will get this parabola, but there is another lower energy state when you vary the gate, which correspond to n+1 charge state, or an extra electron on the dot. And similarly, when you go further, there is another lower point, lower energy point, which corresponds to n plus 2, and so on. So the action of you varying this gate voltage is lowering the levels in the dot down, and at some point of time, the next level, charging level will be available, and electron can fill that level. Then again the dot will go back to, or the island will go back to a lower energy state. So you are filling this island or this box by electrons in discrete manner when you vary the gate. So the number of electrons on this island or dot is represented by this curve as a function of the gate voltage. So at this point, in the one of the bottom of this parabola, the energy level is represented, energy level corresponding to this point is shown here, where this state is full with n electron, and this n plus 1 electron here is empty, but that is high up, so there is no enough energy to fill that state. Now when you vary the gate, you are going to walk through this parabola, but now at this point where the charge, where the gate voltage is going to give you an effective charge of n plus 1 by 2 here, then the parabola corresponding to n electron and parabola corresponding to n plus 1 electron are going to meet at this point. They'll have the same energy. That's a charge degeneracy point. Then an electron, then the dot is equally well whether you have n electrons and plus 1 electron. And if you go further, then you will walk through this parabola here, and this will be a lower energy state. Okay, so the dot will get filled by one more electron, and that goes on. So that is the physics here. So we are going going from a parabola with an electron, and then next parabola n plus 1, n plus 2, n plus 3, but you are going to sequentially fill the island by electrons. Okay, so the electrostatic energy is going to oscillate like this, and whenever these two parabola meet, any of these parabolas meet, that's a degeneracy point, and you can fill an extra electron. When you walk back, you can remove that electron. That corresponds to you are sweeping the level across the source of charges here. To this point, the crossing point corresponds to the charge, the level on the dot, the charging level on the dot is in resonance with the drain, or in resonance with the source of electron. Now, this is the story of single electron box, where you get a step-like behavior in the total charge, and each one corresponds to one charging one electron at a time. Okay, adding one electron at a time. You are going to take the charge state of this island, n plus 1, n plus 2, and so on, sequentially. The same concept and experiment can be done with Cooper pairs also. In this landmark paper, they have done an experiment which is very similar to what we discussed. But here, the island is a superconducting island. Okay. And you have a non-superconducting source of charge. Okay. And there is a thin internal junction, and there is another electrode. Okay. which is going to work as a capacitor. Okay. Now remember, the Cooper pair has charge 2 electron, 2e, not 1e. Okay. What that means is, when you have Cooper pair, the number of electrons on the island should be added 2 at a time. For these, because there are the states are Cooper pair states. Those are not states for electrons on the island. Okay. So you only add 2 electrons at a time. Okay. But when it is in normal state, under the action of a magnetic field, you can bring this island into normal state. It becomes a normal metal. Then this should show 1 electron at a time, or a change of charge E at a time. So you can bring this island from 2 electron at a time to 1 electron at a time. Okay, by varying the magnetic field, and that's what this experiment was. So here you can see, when you have a small magnetic field applied, the steps that we discussed are of the magnitude of charge E, electronic charge. And when you don't have a field, then these are actually twice, these steps are twice in height, or with the charge 2e. That is equivalent to doing that. You have a series of parabola, and these are charge degeneracy points. Okay, and in the normal state, and when you have a superconducting state, these alternate parabola, which correspond to odd number of electrons, they will have higher energy because those are not accessible. So when you remove the field, the odd numbered parabola will not be in the available energy window, because those requires electrons to be present in the system. But when you don't have magnetic field, it's a superconductor, and you don't have any electrons, and you have only Cooper pairs, so those will go up in energy, and that's what is happening as you vary the field. When you apply the field, you are going from this direction, your field is going up. You are applying higher field. When you apply field, this will be a normal state, and this is a superconducting state. Okay. So you are taking the island from superconducting normal, then you can see that the step size is actually changing from 2e to 1e. It's a very interesting landmark experiment demonstrating the Cooper pair box, or single electron box, both of them. Okay. Now, the Cooper pair or the single electron box, if you look at, you have only one tunnel junction, which is connected, and the other side is a capacitor. Now, you can modify the geometry a little bit, and you can get to a very interesting and highly useful and technologically important device called single electron transistors. So what we have is, you have a conducting region, we can still call it an island, this tunnel coupled to source and drain, and so capacitively coupled to a gate with a voltage, and this is going to provide the source drain voltage. Okay, and this is going to provide the gate voltage. Now, when you have low voltage applied on the system, the source voltage is low, as shown here, you don't have enough coverage of this voltage to have the charging level within this energy window. Or you can also say that when you have low voltage, you don't have enough energy to overcome the single electron charging energy required for single electron charging, which is E square by C sigma, because E square by 2 is C sigma for each junction. So E square by C sigma. Okay. Now, when you increase your bias voltage, when you apply more voltage, then when it matches the charging energy or the voltage required to put an electron onto this island, the current will slowly start rising. This is the positive direction and this is in the negative direction. So in this region, there is no current is flowing through, and the current is blocked because of the Coulomb repulsion of an electron of the charge which is already there. That is the basic reason for observing charging effect, or that is the charging energy is there because you have Coulomb repulsion due to the existing charges already there, which is opposing the addition of charges, addition of electrons further. So this phenomenon of no current flowing through is called Coulomb blockade. So in this situation, the source and drain does not have enough potential difference, or the source is not applying enough potential to have an electron on the island and then off the island. Okay, charge and discharge. But in this case, you have enough energy so that the potential difference is sufficient to have an electron passing through the system. But remember, one electron. The energy is sufficient only for one electron. Okay. So in this process, the charge state of the island or charge state of the dot is going to go from n to n plus 1. That is when the electron is here. But the next electron or energy state for the next electron somewhere high up here, which is not accessible by this potential. This cannot put electron there. Okay. This can put an electron here, but in this level, but cannot put the electron here. That requires twice the charging energy. Okay. So it's a sequential process. So you have n electron, then when you put this electron here, n plus 1, when that electron tunnels out, then n back to n again, then the next electron can tunnel in. So, and that process is will go on. Okay. So this process is called single electron tunneling. Single electron tunneling. And this device, which is controlled by, which is three-terminal device, controlled by source, drain, and a gate, which is similar to a transistor, a MOSFET, where you have source, drain, and a gate there also. But this one is operating in a regime where you are going to see the effect of quantization of the charge or discrete nature of the charge. Okay, so this is called single electron transistor. Okay, because the transport happens sequentially, electron by electron. Okay, one after the other. And this effect of not having current flowing through when the voltage is low is called Coulomb blockade. And in this paper, they have observed this charging discharging effect through tin nanoparticle which are deposited on the on aluminum film. Okay, so they have thin tunnel junctions on both sides. This is giving a rough idea of how the energy levels are aligned. So you can see that the resistance as you the differential resistance dV by di is high as you reduce the source drain bias. This is nothing but the derivative of a curve which is going to look like this. Okay, and what you are seeing here is also an effect of temperature, which we will discuss later. But the temperature effect of temperature is to smoothen this curve here. As you increase temperature, this curve will get smoother and smoother because the temperature energy, thermal energy, also will contribute to this tunneling, so that the sharp turn on of this curve will get smoothened by temperature or thermal effects. Okay, and that's what you are seeing here. At really low temperature, the curve is very sharp, and as you increase temperature, it's going to get smoother and smoother and smoother. Finally, it will wash away. It will get washed away. Okay. So here, again, it's a behavior. It's a collective behavior of many nanoparticles. That also is going to add smoothness to this curve. But this discussion is based on one island. Okay. Now, the single electron transistors, as we discussed, are three terminal devices. Okay, so you have source, you have drain, and you have a gate. Okay, now the current through this device we just looked at as a function of source drain bias here. Okay, but we have not really discussed the effect of the gate on this current through the device. So let's look at this energy, total energy versus gate voltage diagram. So you have this parabola, and at the charge degeneracy point, it is favorable for an electron to go on and off the ion, or two charge states are degenerate, or they have the same energy. For example, n and n plus 1 has same energy at this point. Okay. Similarly, n plus 1 and n plus 2 has same energy at this point, and n plus 3 and n plus 2 has same energy at this point, and so on. Okay. And we also discussed that the transport happens in this fashion, that n becomes n plus 1, then back to n. That means at these points, you have the nearby charge states degenerate, and that is the situation here. That is how the transport happens. You fill in, take it out, fill in, take it out, fill in, take it out from the other side. So at all these points, transport can go through, the electrons can go through the system from source to drain. Here, this cartoon shows the energy level alignment inside the dot with source and drain. So it is basically aligned with the source and drain, which makes it favorable for the electron to go through the system. Now, when you increase the gate voltage further, you're going to move to this parabola somewhere here. Then this parabola, this point has this charge state energy, this one has this energy. There's huge energy difference between these two states. Okay, and here n plus 1 is favorable. In this point, n plus 1 is favorable. So the charge state is locked in that position. So you cannot have any transport to the system. And as you increase the gate voltage, you will reduce the current and you will reach a situation where the current is shut down. And you go further, then you are going to go through this parabola and eventually you will reach another point where n plus 2 and n plus 1 are degenerate. Then again you can get a current flowing through the system. And again you will go down if you increase the gate voltage further, and so on. So you are going to get a periodic array of peaks in the current, or you are going to see oscillations of the current as a function of the gate voltage. That is called Coulomb blockade oscillation, because this is arising because of the phenomenon of Coulomb blockade. Okay, and this is an experimental data where you see a periodic oscillation as a function of gate voltage from a representative device. And at this point, we get a peak in the current, and the current will die very soon as you move away from that point. And how fast it will die away all depends upon various other factors such as thermal broadening. If you have higher temperature, then the states can get broadened. The source and drain can get broadened, so you don't have this sharp cutoff like what I have drawn here. So you'll have distribution. So you'll have states here also, which are filled and can populate nearby states. So all those effects will play. But this is assuming that the source and drain Fermi levels for distribution is sharp, and the levels inside dots are also sharp. Okay. Now let's look at the IV characteristics that we discussed in the previous slide a little bit more detail. And we are interested in what happens to IV characteristics when we vary the gate voltage. Okay. So this broad IV characteristics, this the one with the large current blockade region here, is what we discussed. Okay. Now, as we discussed, the current will get turned on when the bias can accommodate one of the levels within its window. Okay. But you can also get that level within the bias window at a lower bias by varying the gate. Okay. So you can apply gate voltage and push these levels up at a lower bias and get this level within the window and turn on that device at lower voltage, even lower voltage. Okay. And finally, you can get it more or less linear, ohmic behavior. Okay. So you have two knobs to play to get the current through device, or to lift the blockade or lift the shutdown. One, you can apply a very large source and bias to overcome the charging energy, or you can offset the charging energy by applying an extra charge through a gate. It's an induced charge for the gate. There are two ways to do that. Okay. So when you apply large source and bias, the current will turn on eventually. But if you push the levels into the window by a gate voltage, then you can turn on the device even at a very lower voltage. Okay. And usually when you measure these devices, you do both in a very interesting manner. You do a combination of both because that information is very, very crucial to understand the geometry of the device. And that is called charge stability diagram or Coulomb diamond. So it's a two-dimensional plot of current versus source and bias and gate voltage, because it's a three-terminal device. You have source and bias and you have gate voltage, and you are running a current through the device. So it's a plot of both. Okay. So what you are going to get is when you vary both, you will get a two-dimensional plot. That plot, the current in this plot, the current is a color, and one of the axis is the source and bias, one of the axis is gate voltage. Okay. This is a cartoon. I will show you the real plots in a minute. Okay. So what we have is you have regions with no current, which are diamond shaped. Okay. So diamond shaped regions of no current flowing through. That is why it is called Coulomb diamond. This plot is called Coulomb diamond plot. And let us analyze this plot a little bit more detail by taking slices through it. So let's run through the middle here. So we know in the middle we have very small bias and you are varying the gate voltage. And that is what you have done before, where you apply very small gate voltage and very small bias and vary the gate voltage, and you're going to get a sequence of oscillations. Okay. That is what you are seeing here. Okay. So at these points where two charge states meet, n and n minus 1, n plus 1 and n plus 2 and n plus 1, they have the same energy because the parabolas cross, you get a peak in the current. If you apply a slightly larger bias, the same thing will happen, but the current can start flowing from here itself. Okay, that means you will get broader peak, but with the same periodicity. Similarly, if you take slices along the x direction, along the bias voltage direction in this plot, then for a given gate voltage, you are going to get a blockade region in the middle, and the current will turn on when you overcome the charging energy. And you can offset this by a small gate voltage as shown here. Then you can reduce the blockade region and you can get current turned on at a lower bias voltage. This is basically the same thing what we discussed in this slide, where you can apply various gate voltage and you can reduce the blockade region. Okay, so what you're seeing is you have maximum blockade here and here. These are not really symmetric. In general, this diamond is not a symmetric diamond. Okay. So you start with the maximum blockade and you can reduce the blockade region by applying gate voltage. Just like what we saw here. You can start with the maximum voltage here, and then you can reduce the blockade successively by applying more and more gate voltage. Then in the two-dimensional plot, you are going to get this slopy or triangle behavior. Same thing happens to other half also. When you add these two together, you will get a diamond shaped region. That's what you are seeing. And if you look at the geometry, which is plotted here, the distance from the center to start the transport, or the center to the onset of transport, that should be the charging energy, because that is what is required to put an electron and overcome the charging and put an electron on the island around the dot. So that should be the charging energy. So just from this dimension of this diamond, you can get the charging energy. Similarly, the periodicity here should be E by Cg, because this diamond differs by one electron. So inside this diamond, you have a charge which is stable. There is no transport, the charge is locked. Okay, so you have n plus 2 to n plus 1, n minus 1, and so on. So the distance between two diamond, or the size of the diamond in the y direction here, should be equal to one electronic charge. So that is basically equal to adding one extra electron. So the delta Vg, that is the width of the, or the height of the diamond, should be E by Cg. So just by measuring the dimension of the diamond, you can actually get the total capacitance C sigma, and you can also get the gate capacitance, or capacitance of that particular gate to the dot Cg. So just by taking this diagram, you can get a lot of information about the geometry of the dot. If you have many gates, you can get the capacitance of all those gates by repeating this measurement with various gates. Okay. So this Coulomb diamond acquisition in a measurement is a very important step, and it is a necessary step to verify that you have a quantum dot. If you have a quantum dot, then you will get a Coulomb diamond. If you don't have a Coulomb diamond, then you don't have a quantum dot. That's for sure. Okay. So this is like a touchstone phenomena, or touchstone measurement, or a proof to show that you have a well-defined, well-behaved quantum dot in your system. Okay. Now, let us look at the Coulomb diamonds of various systems. Let's start with the metallic quantum dot. So there is one confession I have to make here. That is, though I have been calling these are quantum dots, these are actually classical dots, because we have not really discussed anything quantum mechanical so far. The only quantum mechanical thing, or only quantization we have discussed, is charge quantization, or discreteness of the electronic charge. But that is not a property of this quantum dot, that is the property of the charge. Okay. So though we, and also in the literature, you say these are quantum dots, but these are not really quantum mechanical objects so far. Quantum mechanical objects will reveal quantum behavior or wave nature of electrons, which we have not discussed so far. Okay. So, but you can still call them quantum dots, but those are not really quantum dots. Those are basically classical dots. Those are small regions, but not revealing any quantum mechanical effects so far. Okay. So the case here is you have a metallic quantum dot. So in the metallic quantum dot, you have so many states. So the states inside dot are not discrete, as we just looked in. That is for the ease of discussion, but those are actually continuous states, continuous distribution of state. Of course, there is a small energy gap here. That energy gap is not the interlevel spacing or anything. It's basically the energy that is required to add an electron or have the transport going through. Okay. That is that energy gap. It is not a quantum mechanical concept. Okay. Now, in this experiment, what they have done is they have trapped a small nanoparticle, metallic nanoparticle, gold. Okay, the circuit, equivalent circuit is here by electromigration technique, and they measured the Coulomb diamond. You varied the source drain bias and also the gate voltage, and they observed the diamond shaped regions like this, the sequence of series of diamonds. Okay, this is the behavior when you have metallic quantum dot. These diamonds will go on forever. Okay, we'll get many diamonds, almost infinity, because you have that many electrons inside the dot, that many states inside the dot. So you have so many diamonds which are almost identical looking, you will get. Okay, in theory it should be pretty much identical because the density of states is pretty constant in that small range where you are applying the voltage. So, and you have so many late states available. Okay, so you will get identical looking diamonds, infinite number of diamonds. You can swing this gate voltage in a very large range, you still keep on getting diamonds. But that is not always the case. Okay, but this is the case when you have metallic quantum dot. Okay, metallic dot. Okay, now when you have a semiconductor quantum dot, such as the gated quantum dot, the situation is slightly different because you don't have that many electrons as in a metallic quantum dot. The charge density is much lower. That is one thing. Second thing is, quite often you define this semiconductor quantum dot by gating. Metallic quantum dots are defined not by gating. Those are basically made by making the island smaller by various techniques, which we will discuss in one of the coming classes, how to make these devices. Okay, so the metallic quantum dots are actually small islands. Semiconductor quantum dots in general are defined by gating techniques. Gating techniques we have discussed in one of the initial lectures, where you have a two-dimensional electron system such as gallium arsenide, aluminum gallium arsenide, and you are going to put gates on the surface and you will apply negative voltage and you will confine the electrons. So in this specific case, what you have is you have a small conducting region here. Roughly it's going to be like circle or elliptical. Okay, though it looks like squarish, but the overall effect of the gate plus the etching, where you have defined the mesa here, is to make it, the edges will be smoother and it's going to be almost like circular or elliptical. Okay. Anyway, the point here is when you apply voltages on these gates, you will get a confined region in the middle, that is your quantum dot. And this is going to be your source and drain region. Okay. And you'll have tunnel barriers here, which are defined by the gate. So what you have is, you have a tunnel barrier here, then another tunnel barrier here. That is how you are going to define the dot. Okay. And these tunnel barriers height and the width are a function of this voltage on this gate. So when you apply more and more voltage, you will basically make the field reach more and more into the dot region, which will have an effect of making the dot smaller and the tunnel barrier wider. Both effects will be there. So when you have the gate defining the quantum dot first, you'll have a large quantum dot. And when you increase the gate voltage further, that means you'll make this tunnel barriers larger and also wider because of the electric field effect or the fringing field, which is going to eventually have an effect of making the dot smaller and smaller and smaller and smaller. Okay, and that's what you're seeing here in this plot. You started with a large dot. Large dot means capacitance is larger, so charging energy is lower. So the charging energy is nothing but the size of the diamond. Okay, Now when you apply the gate voltage, when you make the gate more negative, that is in this direction, you will reduce the size of the dot, which will have an effect of reducing the capacitance, which will in turn increase the size of the diamond in the measurement. That's what is happening. And as you march down, you are successfully increasing the size of the diamond or reducing the size of the dot. But you're also pushing the electrons out through that process, because every diamond has a stable charge configuration. The nearest diamond will have one electron more or less, depending upon which direction you are going. Okay, so you start with, say, then n-1, n-2, n-3, and so on, and finally this semiconductor quantum dots will give you an opportunity to empty the dot completely. So in this case, here you can assume that this corresponds n is equal to 0. Then, because you know n is equal to 0 because it's not going to close. The diamond will not close back. Okay, it will open completely. So this region, n is equal to 0, then 1, you have to be careful. You need to identify the edge of the diamond, because the current also will reduce as you go to lower number of charges. That effect we will discuss later. So 1, 2, 3, and so on. So you can take the Coulomb diamond, then you vary or sweep the gate voltage until you don't see any more diamond, or you'll open up completely. That is a region which is going to look something like this. Then you increase the gate voltage, make it less negative, and you can see that diamond will start closing. That is your first one, then second, third, and so on. Okay. Here, the semiconductor gated quantum dots will give you an opportunity to exactly define certain number of electron in the dot, which has sort of technological importance when we will discuss the qubits or spin qubits, or in quantum basically bits using electron spins. Okay. A similar experiment here, quantum dots on silicon. This was on gallium arsenide. These are two major systems where these experiments are done. Again, you can see that the size of the diamond is small to start with. Then when you make the gate, when you seed the gate, you can see that the size of the gate is increasing. Okay. Now, this region, you can say this pool n is equal to 0, then 1, 2, 3, and so on. But there is a small caveat here. When you make the gate more negative, you are also increasing tunnel barrier. Then the current that you are going to measure depends upon the height of the tunnel barrier. So you could be in a regime where the tunnel barrier is so thick and so high that the current that you are measuring is so low, the current is flowing through is so low that you cannot measure it. In that respect also, you will not see a diamond. But there are techniques how you identify this, that we will identify this regime, or you characterize this regime, which we will discuss in one of the coming classes. You can use technology such as charge sensing instead of measuring the current, which we will discuss later. Okay, so this is the case with the story with the semiconductor gated quantum dots. So in this lecture so far, we have discussed single electron charging, single electron box, Cooper pair box, Coulomb blockade, Coulomb diamonds for charge stability, and overview the metallic and semiconductor quantum dots. In the next lecture, we'll continue discussing this transport through this topic, the transport through quantum dots, but now we will consider the quantum mechanical effects also. All right.